Year 13, Chapter 9, Further Differentiation, with some links back to Chapter 5, Differentiation, Lesson 5, Implicit Differentiation, Part 1. So let's start off by revisiting differentiation techniques as we know them. If we are differentiating a function with respect to x, I can use what we call the differential operator, d by dx. So I can say I'm differentiating x, for instance, with respect to x, setting out my working like this. I don't have to write y equals x and then dy by dx equals. I can just say d by dx of x is, and this means differentiate with respect to x. So this is an instruction. So differentiating what's in the brackets with respect to x, I differentiate and I get 1. Let's try this, d by dx of x squared. So again, it just means differentiate what we have, which gives me 2x. And let's try a third example, d by dx of x to the power 5 plus 3x. So again, we're applying the differential operator d by dx of x to the 5 plus 3x, giving me 5x to the power 4 plus 3. So far, when we've looked at differentiation, the function being differentiated is in terms of x, and we are also differentiating with respect to x. So the key principle here is that the functions are all in terms of x, and they are being differentiated with respect to x. So we are differentiating a function expressed in terms of one variable with respect to the same variable. Now, it doesn't have to be x. We could, for instance, have d by dp of 3p to the power 4. Now, have a look at this. The function is in terms of p, some variable p, and we are differentiating with respect to p. So this is differentiation as we know it, when the variable being differentiated matches what we are differentiating with respect to. So the answer to this would simply be 12p cubed, and the whole thing is possible, as we keep saying, because the function is in terms of one variable and we are differentiating with respect to the same variable. So this is, to our knowledge, how we have conducted differentiation so far. So what does implicit differentiation actually mean? Well, it means we differentiate a function in terms of one variable with respect to a different variable. Now, an example of this could be if our functions are in terms of y and we're trying to differentiate with respect to x. This would be considered implicit differentiation. So let's go straight in with some examples. D by dx, so I'm differentiating with respect to x, and I'm going to differentiate y with respect to x. Now, what do I get if I differentiate y with respect to x? I get dy by dx, and that's all I can write down. I can't go any further than that, because I'm differentiating y with respect to x, and the result of that is dy by dx. Now, this is really interesting because it actually shows you that the reality is you have been doing implicit differentiation for quite some time. You just perhaps haven't really realised it. So, for instance, if we had y equals 3x to the power 4, and we say differentiate with respect to x, well, it means we're doing d by dx of the left-hand side, and we're doing d by dx of the right-hand side. Now, what is d by dx of y? It's dy by dx. And on the right-hand side, well, the function's in terms of x. We're differentiating with respect to that same variable x, and the answer is just 12x cubed. Now, I suspect when learning about differentiation back in year 12, you could have gone straight from the original function to this without even thinking about it. But the reality was, on the right-hand side, you were differentiating as normal. 3x to the power 4 differentiates to 12x cubed as normal. But on the left-hand side, you were differentiating y with respect to x to give you dy by dx. And actually, that was a piece of implicit differentiation. We need to have a look at some further examples. I would like to differentiate with respect to x, y squared. And the answer is not just 2y, because we're not differentiating with respect to y, we're differentiating with respect to x. Now, learning how to do this comes from an understanding of the chain rule, because we are differentiating a power function. And what does the chain rule tell us? It tells us to multiply by the power. So if this is our power of 2, it tells us to multiply by the power of 2, reduce the power by 1, so it becomes 1, and then multiply by the derivative of the inner function. What is the inner function? It's y, and if we differentiate y with respect to x, we get dy by dx. So the outcome is 2y dy by dx. So can we now apply this knowledge to another example? I would like to differentiate with respect to x the function y cubed. The function and the derivative don't match, so we're doing this implicitly. So differentiating y cubed, again, it's a power function. Think of it like that. Apply the chain rule. We need to multiply by the power, reduce the power by 1, and then multiply by the derivative of the inner function. The inner function is y multiplied by dy by dx. So the answer is 3y squared dy by dx. And you should start to see a pattern emerge. Let's look at a few more examples. Again, each time we'll be differentiating implicitly. D by dx of 5y to the power 7. So the 5 is just a multiplicative constant, so we'll leave that there as part of the answer. The key principle here is that we have a power function. Y is the inner function, which is being raised to the power of 7. So multiply by the power, reduce the power of the inner function by 1, and then multiply by the derivative of that inner function, dy by dx, and we get 35 y to the power 6 dy by dx using the chain rule. And we can make use of the chain rule in lots of different examples when we differentiate implicitly. So d by dx of e to the power y. Now, it's an exponential function. The inner function is y, and e is being raised to that function. What do we know about exponential functions? They differentiate to themselves. So e to the y differentiates to e to the y, but we need to remember our chain rule and multiply by the derivative of the inner function, which is dy by dx. And there's the answer, e to the y dy by dx. What happens if we have d by dx of ln y? Again, it's a composite function, ln of y. What do we know about the chain rule here? It's a natural log function. It differentiates to 1 over the inner function of y. We must then multiply by the derivative of this inner function, dy by dx. So what do we get? We get 1 over y dy by dx. Now, what about the trigonometric functions? Do you think you could write down d by dx of sine y? Again, think of it as a composite with y as the inner function. We know sine functions differentiate to cosine functions, but again, multiply by the derivative of the inner function, and I would probably write that as cos y dy by dx, using a bracket just for complete clarity here. See if you can work out what d by dx of cos y is and d by dx of tan y is. So in each case, y is the inner function in a composite. Cos differentiates to negative sine, but we must multiply by the derivative of the inner function dy by dx, so we get negative sine y dy by dx. Tan differentiates to sec squared, so we get sec squared y, and then dy by dx, multiplying by the derivative of our inner function. Let's try some more complex composite functions. So d by dx of e to the 2y minus 3. So again, the function is in terms of y, and the inner function is 2y minus 3, but it's exponential. So we know it differentiates initially as an overall function to itself. Multiply by the derivative of the inner function. Now be careful, because we're differentiating 2y minus 3, but we're differentiating it with respect to x. So this is where our implicit differentiation kicks in again. What happens if we differentiate 2y minus 3? Well, we get 2 dy by dx. 3, of course, is a constant which differentiates to 0. So the key thing here is we had 2y, which we differentiated with respect to x, and it gave us 2 dy by dx. And you need to go back to the previous examples perhaps to remind yourself of that. So the final answer, 2e to the 2y minus 3 dy by dx. What about this? D by dx of e to the power of y squared. Composite function. Inner function is y squared, but overall it's exponential. We know exponential functions differentiate to themselves, so it's e to the y squared, but we then have to multiply by the derivative of y squared. What happens if we differentiate y squared with respect to x? We get 2y dy by dx. Think back to how we did this previously. So we get this as our final answer. And the answers will start to look quite complex, especially when the original functions are perhaps more complex. So d by dx of ln 2y minus 3. Now it's a natural log, and the inner function in this composite is 2y minus 3. So we end up with 1 over 2y minus 3, and then multiply by the derivative of 2y minus 3. We've actually done that already in the first example in this section, and that gives us 2 dy by dx. Let's finish off with one last example, d by dx of sine 2y plus 5. It's a sine function. The inner function is 2y plus 5. Sine differentiates to cos, so we will initially get cos of 2y plus 5, but we must multiply by the derivative of the inner function, and again, as with the previous examples, we get 2 dy by dx. Having looked at a series of examples, I just want to finish this off by comparing 3 different operations. Now, the first one is d by dx of x squared. The second one is d by dy of y squared. And then the last one is d by dx of y squared. Now, this first one is not implicit. How do I know it's not implicit? Well, the function is in terms of x, and we're differentiating with respect to x. So we simply get an answer of 2x, standard basic differentiation. Now the second one is also not an implicit differentiation. The function is in terms of y, and we're differentiating with respect to the same variable y. So it's a standard derivative. It just gives us 2y as a result. The third one, however, is the one that is implicit. The function is in terms of y, but we are differentiating with respect to x. So what does the answer become? Well, we know it's a power function. Apply the chain rule, multiply by the power, reduce the power by 1, but then multiply by the derivative of this inner function, which is y, and the derivative of y, the inner function, is dy by dx. So there's the outcome of this question. Now, would you be able to do this if we reversed it? So what if it was d by dy of x squared? Now that is also implicit. The function is in terms of x, and the derivative, we're asked to differentiate with respect to y. So what is the outcome? Well, it's a power function with an inner function of x, multiply by the power, reduce the power by 1, so you get down to x, and then what is the derivative of this inner function of x with respect to y? It's dx by dy. So you get a very similar result to previously. So you've got to understand when you're differentiating as normal and what happens if you're differentiating implicitly. Now, we can actually generalize this result in quite a nice way that will help us think about this. Let's suppose we are differentiating with respect to x. So I want to make that clear. And we are differentiating some function which is in terms of y. So another variable. It doesn't have to be x, it doesn't have to be y, but the variables have to be different to each other. So the function being differentiated is in terms of y or some other different variable. Now, think about the chain rule. Start off by differentiating the outer function. So we would do d by dy of f of y, but we then multiply by dy by dx because we've got to differentiate this inner part here. So dy by dx. And that's a general result that we can use. So for instance, d by dx of e to the 5y, well, let's look at the blue part, which tells us to just differentiate this overall function with respect to y. We know that's 5e to the 5y, but we then need to multiply by dy by dx. So the rule applies very easily. Now, if you're not that keen on using the rule, then just do what we've been doing previously, where you look at this, it's exponential, and we know exponential functions differentiate themselves, so you'll get 5e to the y. You then need to multiply by the derivative of this inner function, which is 5y, and that will give you 5 dy by dx. So you get exactly the same answer, just thinking about it in a slightly different way. So, test your understanding of this. Can you differentiate each of these implicitly? Or not, as in the first example. So the first example is not implicit because we're differentiating x cubed with respect to x, so we just get 3x squared. Next example, we're differentiating x cubed with respect to p, so we will get 3x squared, but then we need to differentiate x with respect to p, dx by dp. Next example, we're differentiating x with respect to m, so we're differentiating x cubed with respect to m. 3x squared to begin with, and then differentiating this x gives us dx by dm. Next example, we're differentiating x cubed again with respect to y. So this will give us 3x squared, looking at the sort of outer function. But then again, we need to multiply by the derivative of the inner function, which is this x. So we get dx by dm. And the last example, we're differentiating t cubed with respect to y. So looking at the overall function here, the t cubed, 3t squared is what we get when we differentiate, but then remember the inner function is this t, so multiply by dt by dy. So implicit differentiation taking place in the last 4 examples, but not in the case of the first example. So can we apply the product and quotient rule when we're differentiating implicitly? Absolutely we can. We're going to start off by having a look at the product rule and 2 examples of this. First example, we're differentiating with respect to x, the product x, y. Now, I am quite keen to avoid writing out u equals and v equals here, because we then end up with an awful lot of variables on the page and it becomes very difficult to keep track of everything. Now, the product rule tells us that we need u multiplied by dv by dx, and then we add on v multiplied by du by dx. Essentially, we keep one component the same, multiply by the derivative of the other, and then swap it round. And I think we can do that without having to set out all the u's and v's, which sometimes leads to a lot of confusion as to what is going on. So this is going to be u, and this is going to be v. So we start off by leaving u alone. So that's just x. And then we have dv by dx. So that means we're differentiating y with respect to x, which is dy by dx. And then we swap it around. This time the v tells us that y is being left alone. And this part tells us we're differentiating the u function with respect to x. But x is already in terms of x, so it's not really implicit, that's just going to be 1. So the answer is x dy by dx plus y. Let's try that again. D by dx of a product, my product is going to be xe to the y. So again, I'll identify one part to be u and one part to be v. And we'll apply this rule that dy by dx, so the derivative, is u dv by dx plus v du by dx. So differentiate and then swap over. So first of all, we want u, which is just x, and then we want dv by dx, so that means differentiating this. That's got to be done implicitly. It's an exponential function, so we get e to the y dy. Remember, it's implicit. And then swapping over, we then want v here, which is just e to the y. And then here, du by dx, well, u is just x, so du by dx is 1. So the final answer is x e to the y dy by dx plus e to the y. And it does start to get quite complicated, so do pay attention carefully. Let's take a look at the quotient rule if we have to differentiate implicitly. This definitely becomes more complex. So d by dx of x over y. Now you may want to actually write it as xy to the negative 1 and then do the differentiation using the product rule, which might actually in many ways be a lot easier. We're going to say that's u and that is v. And the quotient rule tells us we need v du by dx minus u dv by dx all over v squared. So let's fill in everything we know. So first of all, v is y. Du by dx means we differentiate u, which is just x, which differentiates to 1. Subtract u, which is x. And then dv by dx, we need to differentiate y with respect to x, dy by dx, and then the whole thing is over v squared, which is y squared. So this simplifies to y minus x dy by dx all over y squared. Let's look at one last example using the quotient rule, d by dx, of y over sine x. So this is going to be u, and this part is going to be v. So remember the quotient rule again. Set everything up. So v, first of all, is sine x. Now du by dx, that's where implicit differentiation has to start off because u is y. So this is dy by dx minus u, which is y. And then dv by dx, well, that's not implicit because v is sine x, so it differentiates to cos x. And then the whole thing is over v squared, which is sine x all squared, or sine squared x. So we can apply the product and quotient rule, but I would advise significant caution when you set up your differentiation here, because if you start writing out u's and v's, you might get very confused about what is going on and what's being differentiated and which the variable is. You might find that you don't get confused, so try it out yourself and make the best decision for you. Now, so far, we haven't actually found dy by dx because we haven't really been dealing with a proper function. We've just been differentiating various expressions. So what we need to do is actually look at how we find dy by dx for a function. So we're going to have a look at a few examples. I'm going to start with the example xy plus x squared plus y squared equals 10x. Now, the key point that I want to make here to start off with is you must not start by writing dy by dx equals ... as a start. You can't do that because the function has not been expressed in the format y equals. All you can do is differentiate each part from left to right. So we're going to take each component here and differentiate it. So xy, first of all, it's a product. So I'm going to start off by leaving x alone and differentiating y. So I get x dy by dx. And then I have to do the reverse. So I differentiate x, which is just 1, and I leave y alone, which is y. See how quickly I applied the product rule to that. I didn't write out any of the stages of the product rule, but I differentiated using the product rule. Now the next one's easy. Remember, we're differentiating with respect to x, so x squared just differentiates to 2x. Now the next one, y squared. We need to differentiate that implicitly. So thinking about it again as a sort of a composite, y to the power of 2, we want 2y and then dy by dx. And then on the right hand side, this is an easy derivative again. It's in terms of x, we're differentiating with respect to x, we get 10. So let's just round up what we've done from the start here. We simply differentiate each term separately, implicitly where necessary. It was necessary in 2 cases, the yellow and the orange. The next thing I'm going to do is collect terms. So I'm going to collect all the terms that feature dy by dx on one side. So there's an x dy by dx, and then there is an orange 2y dy by dx. Everything else will continue to be placed on the right hand side. So that's 10. Subtract 2x, subtract y, and then I'm going to factorise dy by dx here. So I have x plus 2y, and on the right hand side 10 minus 2x minus y, and then this gives me dy by dx, which is 10 minus 2x minus y, and then the whole thing is over x plus 2y. So make sure you've seen what's happened here. So we collected dy by dx terms on one side. We then factorised and divided, which then allowed us to express our final answer, dy by dx, and notice it's in terms of x and y. So if you want to calculate the gradient at a particular point on the curve, you need to know the value of x and the value of y at that point. And we'll be looking at that a little bit later on. Let's look at another example. So again, we just differentiate each term with respect to x. So the first one, e to the 3y minus 1, differentiates to e to the 3y minus 1, but implicitly we need to differentiate and multiply by the derivative of the inner function, which is 3 dy by dx. Now the next one, a bit more complex, it's a product. So I'm going to look at the split across the product like that. Let's leave x squared alone and differentiate y, so it's dy by dx. And then let's swap over, differentiate x squared to give me 2x and leave y alone to give me y. On the right hand side, 7 differentiates with respect to x to give me 0. Now the rest is really some very basic algebra here, because we're factorising dy by dx from these two terms here, and on the right hand side we will have this 2xy term moved across. So dy by dx then equals negative 2xy over 3e to the 3y minus 1 plus x squared. So next one, e to the sine x plus e to the sine y equals 10. Differentiate both parts, well, all three parts with respect to x. So the green part is going to have to be done implicitly. The yellow part, that's easy, but it does still require the quick chain rule. It's an exponential function, so it will stay as e to the sine x, but multiply by the derivative of the inner function, cos x. The next part has to be done implicitly, so e to the sine y differentiates to e to the sine y, but the derivative of the inner function here, differentiating sine y, cos y dy by dx. There are so many layers to this. You really have to think about this so carefully. You're applying the chain rule, implicit differentiation, so many things. The 10 differentiates to 0. Now this one is perhaps a bit easier than the others. E to the sine y cos y dy by dx is equal to negative cos x e to the sine x. Make it very clear as to which part of the function is which. And then let's divide through to find dy by dx, which is negative e to the sine x cos x all over e to the sine y cos y. So we have x squared plus 2y squared equals 4x. So we want to differentiate each term with respect to x. So keep coming back to that. Each term being differentiated with respect to x. X squared is easy, just going to be 2x. We then have to differentiate this part implicitly. So overall, it's just going to be 4y, but then we need to multiply by dy by dx. So again, you're regarding this as your sort of inner function here. And on the right hand side, 4x is an easy one to differentiate, it just becomes 4. So we can then rearrange this, dy by dx is equal to 4 minus 2x all over 4y. And of course we can divide through by a factor of 2 in the numerator and denominator, so we end up with this result here. Now, let's take a look at this. We have x cubed, y cubed, and 3xy. So x cubed will differentiate to give me 3x squared. Y cubed, so we have this inner function of y, which is being cubed. So this gives me 3y squared and then dy by dx. And then on the right hand side we have a product. Now I'm going to split it up so we keep the 3 with the x, so 3xy. Differentiate 3x first of all and we get 3, so we can leave y alone, and then leave 3x alone and differentiate y, we get dy by dx. We could have just differentiated xy and then multiplied it all by 3. That would have worked as well. Now, this is quite convenient. We can divide through by a factor of 3 across all 4 terms, and then I want to collect the dy by dx terms on one side, and all other terms can be collected on the other side. Factorise dy by dx, and then divide through, so we get dy by dx, which is y minus x squared over y squared minus x, which has a rather pleasing symmetry to it. So this is a really interesting example. Look at the left-hand side. It is a composite, and it's a power function. What's the inner function? The inner function is x plus y. Let's start with the fact that this is a power function. So differentiating, and that's what we're going to do, differentiate both sides with respect to x. On the left-hand side, I've got 2 x plus y, reduce the power of 2 by 1 to give me 1, and then multiply by the derivative of the inner function. So that means I've got to differentiate both parts of this. Now x differentiates to 1, y differentiates to dy by dx with respect to x. Now on the right hand side we've simply got 4x, which differentiates to 4. Lots of different ways of going about our simplification here. We can divide through by 2, and then we can say that 1 plus dy by dx is equal to 2 over x plus y, dividing through by that bracket x plus y. Dy by dx is then equal to 2 over x plus y, subtract 1, and then you can simplify that if you wish to 2 minus x minus y over x plus y, combining denominators. Last example, y cubed equals xy squared minus x squared. This is going to have to be done implicitly, so is this, and let's note that it is a product as well. This part on the right hand side here, however, is an easy derivative. So left hand side first of all, y cubed, differentiating with respect to x, we get 3y squared dy dx. Now for this product I'm going to leave x alone and differentiate y squared, so that will give me 2y dy by dx, and then I'm going to differentiate x, which is 1, and leave y squared alone. Now x squared differentiates to 2x. Now let's collect dy by dx terms on one side, doesn't matter which. Let's collect them on the left hand side. What are we then left with on the right hand side? Well, a y squared and minus 2x. On the left hand side, dy by dx out of the bracket, 3y squared minus 2xy inside the bracket. And we can then finish off dy by dx is equal to y squared minus 2x, all divided by 3y squared minus 2xy. Key point here, make sure you really understand how to differentiate these products implicitly.